Hello everyone. So today going on to the new topic, that is the third chapter, classification of elements and periodicity. Today we will see the introduction of how the periodic table formed. Okay. So as you know, what is the need of classification of elements, isn't it? We have studied in 10th standard why you need to classify elements in order to have similar properties. Physical and chemical properties, you want to classify the elements. And the first attempt was made by the scientist, which is called as a Daubonnier, which you call it as Daubonnier triads. And you know what he did in Daubonnier triads. There are only three elements in the group, and there was three such groups, like for example lithium, sodium and potassium. It was a triad. Okay, and also chlorine, bromine, iodine. This is also a triad. Okay, then calcium, strontium and barium. That is also a triad. So these only three triads was formed or discovered by Daubonnier. So that was again a failure. And in Daubonnier triad, what he did, he said the middle element's atomic mass must be the mean of these two elements. That is, the atomic mass of lithium plus potassium by 2 will give you the almost nearly equal to the atomic mass of sodium. Okay. So the middle element has got the atomic mass which is as a mean of first and the third element. It was same applicable to this also, chlorine, bromine, iodine and calcium, strontium and barium. But it was only triads. So it again was a failure, and then again, a scientist called as A.E.B. de Chancourtius in 1682. He also was on the move to classify the elements according to their properties, and he made a cylindrical table of elements. But still, it was again a failure. Then again, some more scientists comes into limelight, and then the other one, which was the most important one, was the Newland law of octaves. That is in 1865. You know the Newland's law of octave. What he said? He said that every eighth element has got the same property of the first element, isn't it? Like sodium and lithium. The first, after this lithium, eighth element is the sodium. So but what was his demerit? Only the Newland law of octave theory was only applicable to calcium. That is atomic number 20. For heavier elements, it was a failure. Okay, and it was same as that of the music octaves, isn't it? Like sa, re, ga, ma, pa, dha, ni, sa, again sa. So it was like the Newland's law of octaves, but it was again a limitations of Newland's law of octave. As you have studied, it was only applicable to till calcium, that is lighter elements, and only 56 elements was discovered until then. So that again was a failure. So next comes the father of this periodic table, which is called as the Dmitry Ivanovich Mendeleev. But at the same time, you are only heard about this Mendeleev, but at the same time, the working of the periodic table was again done independently by another scientist, which is called as a Lothar Meyer. He had also a great contribution to the in setting up the periodic table, like having the same physical property as well as the chemical property, putting into tables, putting into groups and periods and making the periodic table. But when the credit comes, the credit goes to Mendeleev, and then it is called as the Mendeleev periodic table. But the Lothar Meyer also has got a crucial, or he also played a crucial role in doing this classification of elements on the periodic table. Okay, so these are, and you know what Mendeleev's merits and demerits, isn't it? What he did, and he at that time only 63 elements were there, and you know he made a card of all the 63 elements and put the elements having same chemical properties into one, and he named it as groups, and then he studied the properties, isn't it? Then what he made, and he left some gaps. That was the most important thing. He left some gaps, saying that some elements would be found, will be discovered later. Okay, for example, if you are remembering, like he made Ega aluminium. Okay, he named Ega aluminium, and after that, what was formed? Gallium was discovered, isn't it? Ega silicon, for that germanium was discovered. So he put some gaps which shows that again elements has to be discovered. Okay, so that was his major achievement, that he puts gaps in the periodic table. And again what he did in his periodic table, that is the noble gas element, the position of the noble gas element. Without affecting this his periodic table, what he did, that he kept the noble gas in the last group, isn't it? And he made a periodic law. What was the periodic law? The properties of the elements are periodic functions of their atomic weights. First it was the periodic law, then later on it was modified as the modern periodic law. Okay. So then again the Mendeleev he made, then in while classifying the elements or while studying the properties, chemical properties of the elements, Mendeleev found that even though he arranged the elements in the increasing order of the atomic weight, in some cases he had to put the elements with atomic number lesser, atomic weight lesser, because of the similarity in the chemical properties, isn't it? That you have find in the table, the Mendeleev's periodic table. First, when he was put up the first Mendeleev periodic table, it was like that. So he doesn't mind putting the elements having atomic number lighter weight or at a lighter atomic weight in front of the heavier atomic number. Why? Because he want to have the chemical properties similar, and he emphasized on that similarity in the chemical properties rather than the atomic weight. Then there are merits as well as the demerits also for the Mendeleev, because he cannot put the position of the hydrogen in the periodic table. That is, in the first group, hydrogen can be put in the first group as well as in the 17th group, depending on the properties, and all you know. Then then the Mendeleev's the isotope, he cannot have the position of the isotopes, because isotopes are what? Same atomic number but different atomic weight. So it cannot be explained. Okay, and then also there is he cannot explain the gradation, how many elements are coming in between two atomic numbers, isn't it? Sorry, atomic weights. So that was also his limitation. But he made a scientist called Henry Moseley. What is it? Henry Moseley. A scientist called Henry Moseley. What he did is, first he got a straight line graph while he was doing his experiments on the X-ray spectrum. He plotted the atomic number. Listen, atomic number versus the root of nu. What is nu? Nu is the frequency of the X-ray. Now when he analyzed the X-ray spectra, he got a straight line graph. So he plotted the frequency with atomic number and he got a straight line graph, which was, the scientist is called as Henry Moseley. It's very, very important. Then Henry Moseley, when he studied the X-ray diffraction spectra or X-ray spectra, where he plotted the frequency against the atomic number, he got a straight line graph which says that the atomic number was a fundamental property than atomic weight, and thus the atomic number comes into the picture. Now when the atomic number has given that position, or that atomic number is a fundamental property, then the limitations of Mendeleev's comes as the achievement, isn't it? Because the isotope was cleared, then still even now the position of hydrogen atom is being a bigger question, but still the isotopes of this has cleared, and the atomic number for every element there is a unique atomic number. So the two demerits of the Mendeleev comes into the merit when Henry Moseley put the atomic number as a fundamental quantity than the atomic weight, isn't it? So that is how the atomic number has become the fundamental quantity, and based on the atomic number, what happened? The Mendeleev had formed a new periodic law, which is called as a modern periodic law, which states that the properties of the elements are the periodic functions of their atomic number. So that is a modern periodic law. So Henry Moseley was the scientist who says that the atomic number was a fundamental quantity rather than the atomic weight. Okay. So these are all some of the introductions which we have studied earlier in class 10th standard. Now we will see the modern periodic table where the Mendeleev has got into the picture. Okay. Now this is what you called as the modern periodic table or the long form modern periodic table, which was formed by the Dmitry Ivanovich Mendeleev. Okay. Now we will see how he arranged the elements in their properties according to the chemical properties and what was his theory. Okay. Now as the modern periodic table is concerned, it is divided into, or it is formed as groups and periods. See, how many groups are there? There are 18 groups. Okay. Now if you see in this table, in this long form periodic table, it is written as 1A, 2A, 3A, 3B, 4B, etc. But now, as of now, the periodic table, when it comes, it will be like 1 to 18, not A and B. It is just 1, first group, second group, third, fourth, fifth, sixth, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and 18th group. Now, if the periodic table, there is no classification of A and B. Just it goes from first group to the 18th group. Okay, it is not divided into A or B. This is just a little bit long, previous one. That is why it is having a and B. Okay. Now you know the vertical columns are called as groups and the horizontal columns are called as the periods, isn't it? So now how many groups are there? 18 groups are there, starting from the first and ending in the noble gas elements. Okay. Now when you talk about periods, see there are 7 periods in the periodic table. Okay. That is, first period having how many elements? 2 elements. Second period having 8 elements. Third having again 8 elements. Fourth having 18 elements. Fifth again having 18 elements. Sixth having 32 elements, because from this there is a going from lanthanides coming to the 14 elements of the lanthanoids. Then again the 7th period having got again 32 elements. So this is how the configuration goes, and you know how to write the electronic configuration also. In the last class we have discussed detail. Okay. Now we will see. Now here in this 2 groups, that is the first group and the second group, you call it as S-block elements. What do you call? You call it as S-block elements. Okay. Now why you call it as S-block elements, you know, because the valence electrons, the electrons are in the S orbital, isn't it? The electrons are in the S orbitals. So that is called as, that is why we call it as S-block elements. Okay. Then comes the P-block elements. You know, P-block element is, okay. Now this, that is from the 13th group. See, from the 13th group to the 18th group, it is called as the P-block elements. Now why it is called as P-block elements? Because the valence electrons are going into the P orbitals. We have studied about orbitals, right? Orbit and orbitals. Orbital means subshell, like S, P, D and F. So according to the electrons going into the S orbital, you call it as S-block element. Then coming to the P orbital, it is called as a P-block element. Then D-block element. See, from the 3rd group to the 12th group. See, from the 3rd group to the 12th group, you call it as D-block elements. What is it? D-block elements, or D-block elements are also called as transition elements. Now why transition elements? Because it is the transition between S-block and the P-block. Now while going from S-block to the P-block, there is a transition elements which is called as the D-block elements. Now here the electrons are going into the D orbitals. So that is why they are called as the D-block elements. And now coming to the last 2, that is the 6th and the 7th group. I told you from lanthanides or lanthanum, there are again 14 elements. That is starting from cerium and ending in lutetium. These are called as lanthanoids, and from thorium to lawrencium, they are called as actinoids. So these 2 are called as F-block elements. Okay, or you can again call it as inner transition elements, because this is transition elements, and inside the transition elements, that is starting from lanthanum and actinium, again why this is called as inner transition or F block element? Why? Because here the the electrons are getting into the F orbitals. That is why 1 to 14 F orbitals means 14 elements can be filled. So it is called as the F block elements. So it is called this is called as S block elements, the first and second group. P block is 13 to 18, then D block is 3 to 12, and F block is inner transition elements, which is you put it outside the periodic table to make it not confused. Okay, so this is about the a picture of the modern periodic table. Okay. Now we will see some of the elements which are more important to study, and you know the hydrogen having atomic number 1. Now what is the electronic configuration? 1 as 1. So that is called S orbital or S block element. Now it has got 2 elements in the first period. So you see from the first, this is first period. So how many elements? Hydrogen and helium. So that is 2 elements on the first period. Second period, how many elements? See, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. 8 elements are there. The third period also has got the same, that is 8 elements, that is from sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. Okay. From the fourth, that is from the potassium, there are having 18 elements. That means this, from after this, that is after the S block, the electrons will go into the d orbitals. Then after filling the 10 electrons in the d orbitals up to zinc, it will start again from the p orbital. That we will see afterwards how the electronic configuration goes on. Just this is a picture of what is the periodic table. Then now if you look into the periodic table, you know hydrogen. See what is the color of this hydrogen? It is pink in color, isn't it? Pinkish in color, which states that it can belong to the non-metal. But actually speaking, from now if you buy a periodic table, the hydrogen will be here, somewhat here. Neither in the first group nor in the 17th group. It is just in the middle, because it can either be in the first group or in the 17th group. Okay. Now then comes the metalloids. You know metalloids, that is see carbon, that is pinkish color, carbon, nitrogen, oxygen, phosphorus, sulfur, selenium. Now what are metalloids? Metalloids means both, it shows the properties of metals as well as non-metals. So these are metalloids. Then here see the non-metals are there. The first and second groups are metals. Then the P block is non-metals. But see in the non-metals also, while coming towards a group, what happens? The metallic character increases. So when you talk about, for example, the carbon family, you can see lead as a metal. Okay, even though we say that it is a non-metallic group, but while coming from top to bottom in a PT, you can see that the metallic property increases. That we will study later how the metallic property increases or what the reason behind the metallic property. Okay, so this is all about the periodic table. Okay, so I hope you understood. Now you have to study in detail about the electronic configuration of this groups, that is S block, P block, D block and F block. Okay. Now we will see how to write the nomenclature of elements having atomic number greater than 100. You know there are 96 naturally occurring elements have found. Others are all artificial, man-made elements. Many scientists had put forward the discoveries of elements which only having a very few elements are modified. So it is difficult for them to have the naming of that elements. So what IUPAC does is, they have said some scientists or mainly the elements are named after the discoverers, isn't it? Like Einsteinium, or I mean not Einsteinium, some other Lawrencium, etc. So many scientists after the discoveries, they will name their element discovered as their own name. But some confusion comes in between. So the IUPAC has said that no need of putting their names. You can have a IUPAC system of or IUPAC nomenclature or how to write the nomenclature of elements having the atomic number greater than 100. Okay. So what the IUPAC says is, for the digit 0, the name will be NIL, N-I-L. Okay, and the abbreviation is N. So you don't go for this abbreviation, but just you have to note it down. So digit for 0 is, it will be NIL and the abbreviation is N. 1 is UN, UN and U. 2 is bi, B. 3 is tri, T. 4 is quad, it's Q. 5 is pent, P. Then you know 6 is hex, we will say hexa, right? Like hex, H. Then 7 is sept, septa, so sept, S. Then 8 is octa, oct, O. And 9 is N, E-N-N, so E. Now how will you write this? According to this, how will you write the nomenclature for elements more than, atomic number more than 100? So for example, if we have 101, how will you write it? For 1 it is what? 1 it is un, isn't it? Un. 0 is what? Nil. So un, nil. Again 1, 101, right? Un, il, un. Then common is yam. So un, nil, yam. So this is how you will write the name. Now for 102, see un, then 0 is nil, then 2 is bi, then yam. Un, nil, yam. So like that you can write 103. How will you write 103? Un, nil, then 3 is tri, trium. So un, nil, trium. So that is how. So what you have to do is, you have to write the elements from 101 to up to 118. Okay. So how will you write 118? 118 will be un, isn't it? 1, 8 is octet, octium. So un, octium. So you have to write from 101 to 118. Okay, just try it out. It's very easy because you know the name, how to give the name for the digits. So it will be very easy to put on to 101 to 118. Okay. So this is how you write the nomenclature of elements having the atomic number greater than 100. Now we will see. Now we will see how the electronic configuration, or how you will have the electronic configuration of this S block, P block, D block and F block elements. Okay. Now you know, as in the group periodic table, how it is divided. There are 18 groups, isn't it? In the periodic table there are 18 groups and 7 periods, out of which the 7th period is incomplete. You need not worry about the 7th period because incomplete. So there are 18 group and 7 periods. Now when we come for the S block elements, S block elements means what? S block means, that is first and second, isn't it? First and second is the S block element. And what is the electronic configuration of this S block element? It is NS1 for the first group and NS2 for the second group. Now what is 1 N here? N is, you know, see, we have studied what an electron can be defined by its 4 quantum numbers, isn't it? You know the principal quantum number, azimuthal quantum number, magnetic quantum number and spin quantum number. Now what is N stands for? N stands for principal quantum number, isn't it? So here N will be, in the first group N will be 1, isn't it? And the second group N will be 2. Correct. So this is the electronic configuration, that is the 1s1. The outer electronic configuration is that NS1. Okay. So from S block, you know S block, right? Lithium, sodium, that is hydrogen. Hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. Francium being radioactive, we won't talk about that. We just have hydrogen, lithium, sodium, potassium, rubidium and cesium. In all these elements, the outer electronic configuration will be 1s1. Isn't it? 1s1 for hydrogen, 2s1 for lithium, 3s1 for sodium, 4s1 for potassium, 5s1 for rubidium and 6s1 for cesium. That means the outer electronic configuration is 1 electron in the s orbital. but the principal quantum number differs according to the period. First period is 1, second is 2, like that. Now when you come to about the second group in the periodic table, you have beryllium, isn't it? Magnesium, calcium, strontium, barium and radium. So this is a radioactive, so we don't talk about that. So beryllium. So it has got an outer electronic configuration as NS2. NS2. It's a stable configuration, right? For s orbital, how many maximum number of electrons can be accommodated in the s orbital? Only 2. So here it is NS2. So for beryllium, you will have 2s2. Then for magnesium, it is 3s2. Then calcium, it is 4s2. Strontium, it is 5s2. And barium, it is 6s2. So that is the outer electronic configuration of this s block elements, isn't it? So it will be NS2, that is NS1 and NS2. So this is the electronic configuration of this s block elements. Now we will see what about the p block. And you know the p block starts from 13th group, isn't it? 13th group. Okay. So p block stands for 13th group. So 13th to 18th group we call it as p block elements. These are you know, but still elements. So p block from 13th group, what is the 13th group? 13th group is boron, isn't it? Boron, aluminium, gallium, indium and thallium, isn't it? So this is the 13th group. 14th you know, carbon, silicon, germanium, tin and lead, isn't it? Now nitrogen. Nitrogen is nitrogen, phosphorus, arsenic, antimony, bismuth. Then oxygen, sulfur, selenium, tellurium and polonium, isn't it? Then comes fluorine, chlorine, bromine, iodine, astatine. Okay. And the last is, here comes helium, then neon, argon, krypton, xenon and radon. So these will come from these will have the p block starting from boron ending in the noble gas element. Now if we consider the electronic configuration, what will be the electronic configuration? This is having second period, right? First period is only hydrogen and helium. So this is the second period. So second period, what happens? Second period, it will be NS2 NP1. See, this is NP1 because since the outer electron or the valence electrons are going into the p orbital, then here what happens? In this 7 cases or the 8 cases, the p orbital will be filled. For example, this is NS2 NP1. Here it is NS2 NP2, isn't it? Because it is what? 4. Then 5. Atomic number 5. That will be NS2 NP3. Okay. Now you know what about the peculiarity of P3? P3 is half filled stable, isn't it? You know Px, Py, Pz. Now according to Hund's rule, a maximum how many? 2, then 3 orbitals 6. So 6, the half filled is 3. So this is half filled stable. Oxygen is NS2 NP4, fluorine is NS2 NP5 and the neon is NS2 NP6. See, a stable configuration is attained. So the general configuration is NS2 NP1 to 6. See, that means P block means what for S block it is NS1 to 2 because there are only 2 groups. First is NS1, second is NS2. In the P block, the S orbital is already filled, then only P orbital will fill from 1 to 6. So you can write a general configuration as NS2 NP1 to 6. Okay, so in all these cases it will be like that. Only what is the change? The change is only in the principal quantum number. If it is 2, you can write 2s2. For 1 there is no p orbital, right? So there is no confusion. But in the second group it is 2s2 2p6. When you come here, that is neon. Then 3 means 3s2 3p6 argon. Then krypton is 4s2 4p6. Okay, and xenon 5s2 5p6 and radon 6s2 6p6. So like that it goes on. Only the principal quantum number changes. But the general configuration is filling from 1 to 6. So NS2 NP6. Okay, so general configuration. Now coming to the configuration of the D block elements. Okay, you know the D block elements. Okay. In the D block elements, the general configuration is, you have to study this because this you not studied in smaller classes. Okay. The D block general configuration is n minus 1, listen, n minus 1 D 1 to 10. Okay. Then n s 0 to 2. Okay. n s 0 to 2 and n s np. NP 6. Okay. So that is n minus 1 D 1 to 10, NS 0 to 2 and NP 6. So this is the general configuration of the D block element. Now what is important is, that is in the D block, see, if it is 4, if it is a 4s element, n minus 1 is what? 3D. So starting from 3D, there is no 2D, right? There is no 2D, there is only 3D. So starting from 3D, then 4s, then it goes on like that. Okay. So the configuration is n minus 1, 1 to 10, n 0 to 2. P is not necessary because D orbitals there is no P, only P is coming from the P block. So n minus 1 D 1 to 10, then ns 0 to 2. So this is the configuration of D block element. Okay. So that is, if from the 4s orbital the 3D starts, you know from the Hofbauer principle, right? The 3D has got, a 4s has got a lower energy than the 3D. So the configuration goes like this, n minus 1 D 1 to 10, ns 0 to 2. Okay, ns can have a value of 0 also, that you will study later in the transition elements, and 2. Okay, so this is the general electronic configuration. So please study this, it is important. That is n minus 1 D 1 to 10, ns 0 to 2. So this is the general configuration of D block element. Okay. Now we will see what is the general configuration of the F block element. Okay, how you can write the general configuration of the F block element. Okay, now it is like n minus 2 F 1 to 14, n minus 1, it is D 0 to 1 and ns2. See, this is the general configuration of an F block element. That is n minus 2. For example, it comes from 5. Okay, it is, if it is 5D, see, if it is 4s2, sorry, if it is 6s2, it is 5D and 4F. Because only 4 it starts from F. That is, n is equal to 0, 1, 2, 3, S, P, D, F. Okay, so 4F, 5D and 6s. So this is the configuration of a F block element. You just study the configuration, general configuration. For 1 mark question it can be asked, write the general configuration of D block element, or D block element, or write the general configuration of F block element. Okay, so that's all. You have to just study that P block element is ns2 np6 and 1 to 6, and S block is 1 to 2, ns 1 to 2. D block is n minus 1 D 1 to 10. What this means? The D orbitals are filling, the 10 electrons are getting into the D orbitals, and here the F orbitals are filling from 1 to 14 electrons in the F orbital. Okay, so these are the general electronic configuration. Okay, just remember. Okay, now we will see detail in the D block element, how it starts from scandium to zinc. Okay, so we will see in detail how it goes, how the filling goes, etc. Now we will see group wise. So what is group wise? As I already told you, there are S block, then P block, D block and F block element, isn't it? So there are 4 groups. We will see that in the next class. Okay, so we will see the details. Now these are all only the introductory part. Now the real part is the periodic trends. So that you will see in the next class. So just have a go through in the book. Any doubt, just follow. Okay. So thank you.